So thanks again, and thanks to you for resisting until the last day. So the goal is, we have one main goal, which is to finish the calculation that we started for the XX chain. I think it's quite instructive, pedagogical, and also beautiful. And then in the time that remains, hopefully I'll try to say something about interactions. Okay. So let us remember where we stand. So we have a general formula for the von Neumann entropy as a function of the 2-point fermionic correlation functions restricted to a subsystem A, which is the subsystem of interest. Okay. And then ideally we would like to compute this formula, to evaluate this formula in the limit of large time and large sizes of subsystem A. Okay? This is complicated, so we start with a simpler task of computing the moments of this correlation matrix. Here n is an integer. Okay? So what is the correlation matrix? As this structure here, so it's written in Fourier transform. Okay? And this GKT is the Fourier transform, indeed, of the correlation function. Okay? In this case, for the null state, as this form, okay, where epsilon is the single particle dispersion of the model. Okay, it's cosine or minus cosine. Okay. Doesn't matter. So last time we arrived. So we started with M2. So M2 is the second moment of GA. And we wrote M2 in this form. L over 4 square integral dk1 over 2 pi, dk2 over 2 pi. Then we have an integral over some auxiliary variables, minus 1, 1, xi1, xi2, e to the minus I L xi1 minus xi2, k1 minus k2 divided by 2. Okay, this is just a bunch of phases, and then here we have some trivial functions. Yeah, of course, I'm not using it. K2 minus K1, and then here we have the trace of GK1 dot, product GK2, okay? T, if you want, there is a T here, okay? So, okay, this is where we stand, okay? These W's are you remember, as sine K over sine K half. Now you want to use the stationary phase approximation. Okay, remember that time is hidden here, which introduces a bit of complication. Okay? But L is here, so for L large, if you do the stationary phase approximation with respect to the size variables, okay, you argue that K1 is going to K2, okay, or vice versa. This means that everywhere in this integral, we can replace from the beginning K1 with K2. Okay? This is very convenient because then these functions here, they give just a factor of 2. Okay? So we can replace everywhere K1 equal 2, except here, because here there are the phases. There are this e to the I 2 epsilon kt, and there we have to be careful. Everywhere else we can replace K1, K2, but here we have to be careful. Okay? So let us also do something convenient. So let us define, a new variable z0, which is equal to xi1, and z1, which is equal to xi2 minus xi1. Okay? This is because this integral always depends on the difference between the xi's. Okay? Okay. Then we can integrate over z0 because the integration is trivial because it doesn't depend on z0, right? And here, this is just z1, okay? Okay, so this has become, we change it to z1. Z1 goes from -2 to 2, okay? Z0 is integrated over, but it leaves back a piece, okay? It leaves some mu of Z1. Because you know, Z1 is defined as the difference, so you have to be careful about the integration domain after you integrate over Z0. Okay? And it's a trivial change of variables, okay? And this mu is actually important. Mu Z1 is just the function. I mean, it looks complicated, but it's actually simple. Yeah, here is 1. Looks horrible, but it's actually simple. So if you plot it, let me plot it here. -2, 2. Here is 2. And it's 0 everywhere else, okay? Just a cusp. Okay. Now, so what we want to do, we have to take care of this object here. So what you can do, you take Mathematica, you expand this thing. So if you expand this thing, so you get a term that is not dependent on the phases. So it's 1/2, and then you get 1/4 plus another one, which is essentially the same, in which you exchange, sorry, here there's time. Okay? Just algebra. Okay? Now you see, here you have this interesting alternating phases. This term doesn't depend on time, so essentially we can immediately take care of that. Okay? If we do this integral here, taking only into account this 1/2, then the stationary phase approximation tells you that this Z1 has to be 0, because there is and then this mu is equal to 2. Then if you put all the factors together, you get decay, and here, let me put it inside. Okay, you get this. Okay, it's trivial. Okay, but here we have to add this term here, the effect of those two. Now we have to do the actual stationary phase approximation. Now you see that you can anticipate that both, actually it's not so trivial, but both terms give the same contribution. Okay? So let's do the stationary phase. So if you want to do the stationary phase of this, of course we have also the term. So you have to, in the phase, you have e to the I L Z1 K1 minus K2 half plus 2I epsilon K1 time minus 2I epsilon K2 time. Okay. Then stationary phase, if you do the stationary phase with respect to Z1, you get again K1 equal K2. If you do the stationary phase with respect to one of the momenta, you can choose one. Okay, one of the momenta remains because in the end you will have an integral. Okay, then you get essentially you get stationarity implies that Z1 is equal plus or minus v k t over L, okay? Yeah, okay. Okay? Where v is the derivative of epsilon with respect to k. Now you see where these velocities appear, okay? So the velocities are, so let me write it here. V of A is dk d over dk of epsilon k, okay? And the plus and minus is to distinguish the two terms. Okay? Now you see that the function mu, this object mu that we defined, is non-trivial, because now z1 has that non-trivial value. But still, I mean, it's easy. So now mu, mu becomes max of 0, 1 minus 2 vk absolute value t divided by L. Okay? Now you see we start getting some terms that look like a quasi-particle picture. Like, okay? So you put everything together, and then, so I'll do it here. So m2 is equal to L integral over dk over 2 pi 1/2 plus 1/2 max of 0, 1 minus, yeah, okay, 1 minus, depends where you put the L, but okay, fine. Okay. Mm-hmm. Yeah. Okay, you get this. Now you remember that we have to send L into L half because we have the two-sided unit cell. But we also send V in B half, so this term doesn't change. So the effect is that here you have a L half. Okay? So another thing that you can do is to massage a bit this. Okay? This is convenient. So this is the same as, I hope I did it correctly, but I think it's this, no? Because max of something, of 0 something is, oh shit, I forgot. Let me find it. Well, let's keep it this way, okay? In the end, I will change it anyway, okay? What is the? Ah, it's behind the. Ah. I mean, there is not much difference, okay? Okay, now this is the first step. Now the problem is that. So you see, I mean, if you plot this actually. If you plot m2 divided by L versus t divided by L, you see it starts as 1/4, it grows linearly, sorry, it goes down linearly up to a time which is 1 over V max, something like that, okay? And then it saturates to a value which is no, sorry, it starts at 1/2 and then it goes to 1/4. Okay. So it doesn't look like anything like the von Neumann entropy. Okay, but okay, this is the first step. Now, we have to be more brave and compute Mn. Okay? And now some kind of miracle, not a miracle, but something, I mean, this calculation simplifies a lot. So you start from something horrible, which is a 2n dimensional integral. Then you use the stationary phase again. Then, I mean, all the momenta become equal. This remains true. Okay. Then, I mean, the tricky part is that you have to, I mean, you have to expand. Now you have a trace of gk1, gkn. This produces a lot of terms. There is always one term that has no phase, and all the other terms will have phases. The phases will have an arbitrary number of momenta, always in pair, but always even number of momenta, but there will be all of them. So terms with two phases, with the 2 epsilon, 4 epsilon, 6 epsilon, 8 epsilon. You can check with the Mathematica that they will always be alternating. Miracle, when you do the stationary phase, they give the same contribution. All these terms, they all give this function max here. This kind of cute. So again, the calculation is simple, is similar. You will have a term without a phase, and then all the term with the phase, with any type of phase, will give the same result, max time a prefactor. Okay. 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 So let me. Now at this level, actually, we can a bit more. I mean, now that we realize that things become simpler, we can be a bit more ambitious. So instead of considering this this object here, we can actually consider a more general one. Okay, in which let's say, I mean, you have in which, for instance, here, instead of this, you put an arbitrary function. I mean, A11. Here you have A22. Here you have A12, A21 function of momenta. Okay. The calculation, you see, it's similar. And now Mn, in the end, what you get is L-half dk over 2 pi. And then you get A11 to the n plus A22 to the n. Yes, plus. Let's call it lambda plus to the n plus lambda minus to the n minus A11 to the n minus A22 to the n times, well, the max function of 0, 1 minus 2 vkt over L. Okay. Where all these functions, A, lambda plus, lambda minus, they are function of momentum. So what is, okay, A11, it's the entry 1, of the Fourier transform. Lambda plus and lambda minus are the eigenvalues of, so lambda plus minus are the eigenvalues of gk t. Okay? So it's the 2 by 2 matrix, so you take the eigenvalues. Here I should stress something important. So what did we already started learning something, okay? We learned that whenever there is a phase factor, you get this max. So what does this mean? It means that the dephasing, what does the dephasing do? It gives the motion to these quasi-particles. Okay? So then when you compute this lambda plus and lambda minus, you can take, instead of gkt, you can take gkt slash, well, which is actually jk at time equals 0. Because you know what the phase factor gives. The phase factor, the effect of the phase factor you accounted for in this max. Okay? Is that clear? I mean, it's difficult, I understand, but, I mean, not difficult, but you have to do at least this calculation once to appreciate that you can do this. I should say that it's not always the case that things are so simple. So if instead of computing the von Neumann entropy, you compute something that is called relative entropy, or you compute some reduced Loschmidt-Echo, so which is something like this. So imagine you want to compute trace of rho A t and rho A at time 0 at 2 different times. You can repeat this calculation. But then something weird happens. So what happens is that depending on the n here, you will get terms with different velocities. So each mn has a different dynamics. Then you cannot resum everything, okay? Actually, you get particles with n times v. So it means that as you increase n, the velocity goes up, which is a bit weird, okay? You don't violate any Lieb-Robinson bound, so it's fine. But okay. Also, the same happens if you compute the full counting statistics, okay? But for the entropies, it's not happening, okay?
Sorry, question.
Yeah.
So the lambda plus and lambda minus appear there, but are these just numerical factors? Because there was nothing really from this matrix there that seemed to appear in the prefactor.
No, I mean, if you send A11 to 1/2 and A1 to 2 to 1/2, then you should recover that.
And the lambda plus and the lambda minus are function of this.
The lambda plus and lambda minus are the eigenvalues of this matrix in which you set the phases to 1.
So it's just
Yeah, it's a numerical factor. Yeah. In principle, here in these cases, they were not depending on, you see, this 1/2 doesn't depend on momentum. But in general, for generic quench, you can have some function of momentum. Okay?
Maybe some other question as well. So this G, this was related to this two shift invariant state, like the 1, 0, 1, 0, right? It was specific.
This G.
Yes.
Okay, that's a good point. I mean, it has a 2x2 structure because you have these two side shift invariants. If you have a full translational invariance, then it's a number, a function of k. Then depending on the unit cell that you put, it becomes 3x3, 4x4, whatever size.
Why were we specifically looking at this two shift state?
No, it's just because it's simple. It's not that...
It's not like the ground state of the system.
No. This is an arbitrary state in which you decide to prepare your system and then let it evolve. For the experts, I mean, this is actually not so far from what you will get in the Ising model. There you also get, for generic magnetic field quenches in the Ising model, you get a 2x2 matrix, but there you get for a different reason because you have Majoranas and so on. But technically it's very similar. Okay, so now you see you should, again, stare a bit at this formula and then you say, haha, I mean, I have this. This means that now I can compute an arbitrary function of f of g. Because I have this for any n, I can imagine of expanding f in Taylor and then resumming the series. What does it mean? It means simply that decay over 2 pi. So let's see. Okay. This. Okay, I have the usual max function, okay? Well, let me write it, okay? And then I have plus f of a11 plus this. Okay. I can bring inside the function f. Simple. No? Now, I mean, we can compute everything, right? So, now let us rewrite this. Now I should be able to reconstruct the formula. So f of g a is equal L half integral over dk over 2 pi integral of dk over 2 pi, and then this should be simply, you can rewrite this as I hope there is a m minus, so yeah. Okay. This is just splitting this max as a 1 minus mean or something like that. Then you see that these terms here cancel. So here you remain with a max, and here you have a mean. This should be a trivial if you plot it. Okay. Now we can compute the von Neumann entropy. What is the von Neumann entropy? You have to choose if you choose this function f, this amounts to, this is the von Neumann entropy. Now what happens? So what is this object? This object is just, so this object here is just the trace of f of gk. Right? You apply the function to g and then you take the trace. What is this? What is this? This would be the entropy of the full state. Because, I mean, the Fourier transform is just a unitary transformation. When you compute the entropy, I mean, a function of, you know, I mean, the unitary goes away. So, okay, it's just the entropy of the full system. What is the entropy for the full system? 0. Okay? So this term is 0. And you remain with this. And this is the structure of the quasi-particle picture. Okay? Right? This is the formula of the quasi-particle picture. Okay. Now let us comment a bit on this. So. Okay, I think we're going good. Okay, let us comment a bit on this formula. So, you see, there is a very tempting interpretation. Okay? So, what is this term? This term, so if you have your subsystem A, so let's call this hydrodynamic interpretation. So what is this max? Well, now restore the factor L, but to vkt. So if you have your subsystem A, this is essentially counting the number of pairs that are within A. This is equal number of pairs within A. So the system produces pairs. So as a function of time, the pair leave the subsystem. This here is L. So 2 vkt is the number of pairs that leave the subsystem. So that do not entangle any longer. Sorry, actually that entangle because so this L minus Vt is the number of pairs that are fully contained in A as a function of time. So the number of pairs for which the two particles forming the pair are within A. Instead, this mean of 2 vkt L is number of, as we knew from before, the number of shared pairs. Shared pair means that only one particle is in A. And now you see this formula tells us that for a generic function of GA, we can assign a contribution due to the pairs that are fully contained in A, and a contribution from the pairs that are not contained in A, fully contained in A, okay, that are shared. For the von Neumann entropy, then this, because of the careful choice of the function f, this contribution is not there, because you want to measure entanglement, and entanglement has to depend on these shared quasiparticles. Okay? But if you compute a generic function, then you have both contributions. Okay? Now, what are these contributions? You know, this formula has a simple structure. So max so the contribution to this, you see, is the trace, as I was saying before, of f of gk. I call it slash, okay. I could have said 0. So, okay. And this mean the contribution is, imagine of having gk of t slash, which means 0, sorry, anyway. What is, you have f of a11 and f of a22, which means that you trace either the first row and first column or the second row of second column. Okay? Okay, both contributions here, of course, the velocity is the same because these are related to the modes k and k minus pi, and then the velocity will be the same. But anyway, except for a sign, okay? So this brings us to some, you know, doing this calculation is nice because it gives you an idea how to then conjecture new formulas. So in much more complicated situation for which you wouldn't be able to compute this. So what is the idea? So you can do a kind of local density approximation, or again hydrodynamics So you can imagine you have your system, then you divide it in small cells, okay? Mesoscopic cells, where mesoscopic means that they are small compared to the total system, but still large compared to lattice spacing, okay? Such a way that you can have some relaxation mechanism within the cell. So if the system is homogeneous, in each cell, you can imagine of having some g of k, because each cell is like an infinite system. So you have g of k of t. It's a 2 by 2 matrix, okay? Sorry. Okay? Now, so what did we learn? So each cell then produces pairs, okay? And these pairs spread. This g of k contains the correlation between the pairs. Okay? So as I was saying before, we can remove the time dependence because we treat the dynamics of this quasi-particle in this hydrodynamic way. Okay? So we can forget about the phases in g of k. Okay? And then we can let the particles propagate with their velocity v of k. And this happens in every cell. Now, imagine you have your subsystem A somewhere, and then you want to compute a function f of GA. What do? You use this, this picture. So you imagine that in each cell there are these quasi-particle propagating. So then you have to distinguish the configurations in which in A you have only one member of the pair, okay, of an entangled pair produced somewhere, or you might have also, both members of the pair. Okay? How do you then the formula essentially, well, the formula is that, okay? And then you have to count the number of configurations in which the pairs are shared, which is this minimum, okay? And the number of configurations in which both members of the pair are in A are this max function. And then how do you assign the contribution to both of them? You essentially imagine so for the mean, you have just to take, you trace in this 2 by 2 matrix the degrees of freedom that do not correspond to particles that are not in A. So if both members of an entangled pair are in A, you have to keep the full matrix and compute the trace of F. If only one member of the entangled pair is in A, you have to trace the rest, and then you're left with some entry here. This looks simple. In this case, we don't gain anything. But imagine now we have, instead of pairs, multiplets. Then this looks much more complicated to do. But with this argument, it's easy. Because now this GA is a n by n matrix, where n is the number of species. Now you have several configurations depending on which. If the full multiplet is in A, if only one member of the multiplet is in A, and so on and so forth. Okay? And each of these configurations will give a different kinematic factor, max, min, somewhere. Okay? How do you assign the contribution? You trace out the species that are not in A, and you compute your function f. Okay? This works. So it's a bit surprising, but it works. So essentially, you're able to compute any function of, you're able to use these hydrodynamic arguments to compute any function f of the 2-point function. Another situation in which this works is if you have an inhomogeneous system. Okay, imagine that your initial state is not homogeneous. Then this G depends on X. It's not a big deal, because then you can do the same. You can just do the same, okay? So it works here, even for the bipartition protocol in which you start from from a state which is made by joining two homogeneous parts, the calculation is not easy, but this argument is quite simple. It allows you to get the result immediately. So another thing that you can do is you can study quadratic. This works also for bosons. For any quadratic model, this type of things work. You can also study dissipation. So you can, instead of having unitary dynamics, you can put a Lindblad dynamics. This works as well. Okay? So for Lindblad dynamics, in fact, what happens is that since the system is mixed, the full system is mixed, then this term here gives a contribution always, if you compute entropies. You can even compute negativity, which is quite trickier. And here, of course, this term will vanish because, yeah, negativity is sensitive to entanglement only. Okay? I mean, there are all sorts of things that you can do. It's quite, I think it's nice. You really see hydrodynamics in this setup, how hydrodynamics works. So something that I find interesting is that you see, I mean, in aerodynamics, usually you think of, diagonal correlators that get propagated, you know. Here, we are also propagating off-diagonal elements of G of k. So somehow in free fermions, you are allowed to also propagate off-diagonal correlations between fermions, okay? This is clear because then, I mean, otherwise, this trick of tracing over species wouldn't work. Because here you would have, a lot of matrix elements, okay? But then, what I want to stress is that, you know, this is also nice because you can see, so these off-diagonal elements usually, they dephase. You might say they are dephasing, so they don't do anything, they go to 0. But then you see that in this G slash, you have to keep them. So they dephase, but they are responsible for the creation of the entangled pairs, okay? So they have an effect. So the dephasing destroys most of the details, okay? Most of the correlations, but this robust pair structure remains, okay? At least in free models, okay? Then what happens in interacting systems is the subject of the last 15 minutes, okay? Now I'll make Milos unhappy because
you have 15 minutes.
I have 15 minutes, I know. So let's learn better answers in 15 minutes, okay? We won't be able to understand everything, but, no, sorry. Before doing that, I have to take 5 minutes to explain something else, okay? So let's consider these pairs, okay? So I have to rewrite the formula. S is equal to dk over 2 pi. And then we have some function f of A11 min 2 vk t over L. 1, here is L over 4. Okay, was L over 2, but there is a factor 2, sorry. And I put only f A11 because FA22 is the same. And then here the integration is from minus pi, okay? So there is a factor, it's okay. But what is A11? Is the occupation density of the C dagger K, CK, okay? So this is just so NK is equal C dagger K, CK, which is preserved during the dynamics, okay? Now, I told you at the beginning that this object here, so this is just minus n of k log of n of k minus 1 minus n of k log 1 minus n of k, okay? What is this object? This is the entropy, the thermodynamic entropy of the GG, okay? So how do you see that? Now I'll be a bit quick, but so where did I put it? Yeah, here. So how do I see this? So let's go back to the dispersion relation of the model. So we have this minus cos k dispersion. And then if the system is finite, this means that I have equally spaced values for the energy, Okay, this spacing is 1 over L. Then n of k tells me what is the occupation of these modes. In the case of the Nel quench, n of k was equal 1/2, okay, which means that all the levels were half populated. Okay, the number of occupied level is just L integral over dk over 2 pi n of k. You see, if n of k is equal to 1/2, you get L half fermions occupied. Okay, L half. Okay. Now, as the system approaches the thermodynamic limit, okay, I have somehow to count, okay, what are the possible ways of occupying this band by keeping n of k final, n of k fixed in the thermodynamic limit, okay? How do we do this? So this is actually a nice, simple calculation. So the number of occupied modes between nk and nk, between k and k plus dk is L and k dk. Then, okay, yeah. The number of unoccupied is just 1 minus that, okay? L 1 minus nk dk, okay? And then this is just, if I take the factorial, I have to do the binomial, okay? This is what I'm going to do. Okay? And I have L nk dk factorial times L1 minus nk dk I think I put dk here, okay? Factor, okay? This is just, you know, it's a simple trick. So just you have L boxes, and then you want to occupy, yeah, it's simple, no? Then you do, in the larger limit, I mean, you can use Stirling, and then you can actually show that you get this formula here. Okay? But, I mean, what did we do? We counted the number of ways of occupying these levels. Okay? So essentially, what we counted is, what we computed is the entropy. Okay? This is nothing more than the entropy. Okay? If you want, is the number of each way of filling these spots corresponds to an eigenstate. So we computed the number of eigenstates that correspond to fixed n of k in the thermodynamic limit. And this, by definition, the number of eigenstates is just e to the L times the entropy. Okay? So this object is the entropy of the GG that describes the steady state. Okay? Because the GG, I mean, this n of k for each k are conserved. So the GG is defined by giving these occupations. Okay? If you have multiplets, then you see, we got this because our matrix is 2 by 2. Because then by tracing, we are left with the diagonal elements, which are the densities. But if you have an n by n matrix, when you trace, you have some off diagonal elements. So there is no way the contribution to the entanglement entropy to be the thermodynamic entropy of the GG. Okay? Now let's talk about, let's discuss a bit quickly interacting models, okay? So in the remaining 5 minutes, 10 minutes, sorry, I should say that this, the original calculation where these techniques have been put forward is of 2008. It's Maurizio Fagotti and Pasquale Calabrese. But then it has been, this by now is a classic, but it has been used so many times. Okay? So let's go to interactions. XXZ. Now the Hamiltonian is the same as before, roughly. 1 over L, SI plus, minus, plus, Hermitian conjugate, plus, sum over I, sum delta, okay, yeah. So is the Hamiltonian of before plus this new term, delta sigma z, sigma z. These new terms break the solvability via free fermion techniques. Okay, so the model, if you do the Jordan-Wigner, this would map to some interacting, to some non-quadratic fermionic object. So it will be a quartic term, so it will be interacting. When you see a quartic term, you are in despair because it's interacting, and there are not so many interacting solvable models. Okay. Okay, here we are lucky because thanks to Bethe in 1931, he was in Rome, he was enjoying the sun, and then he decided to do Bethe ansatz. So this thing by now is almost 100 years old, okay, but still giving a lot. So how do you construct eigenstates of this model? So you have to solve some Bethe equations, so-called Bethe equations. I hope Milos will not shout at me. I hope I'm writing them correctly. This minus sign, okay, whatever, just. Now, this is a set of highly nonlinear, complicated equations for the k alpha, which are essentially the momenta, okay? Now, if there is no interactions, sorry, this I think is for delta equal 1, yes. So I anticipated you. So this is for delta equal 1, which is still, interacting and non-trivial, okay? Now, if you don't have interactions, this term here is essentially 1. And then you see that the solution is just the 2 pi over L integer, okay? If delta is different from 0, then you have this term here, which you see it involves interaction between the different momenta, between pairs of momenta, okay? This makes life more complicated. But some things are simple. So the energy, for instance, is sum over alpha cos k alpha. Well, there is a minus 1 here, whatever. Okay. Alpha from y to x. So you see, the energy is just the sum of some function of the momenta. But what is the complication? The complication is that if you draw, you have the same dispersion as before. But now, the k alpha have to solve this equation. And the k alpha, they fill each other. So the spacing between the k alpha is not constant anymore. This is the effect of interactions. So they will fill each other, they will repel, attract, whatever. So the spacing between the levels is already something non-trivial. Before, for free fermions, was just 1 over L. Still, you can construct eigenstates, okay? There is an explicit formula for the eigenstates, which I don't show you because it's actually, even computationally is hard, because it involves a sum over permutation. So You cannot construct explicit wave function for Bethe-Ansatz solvable models for chains more than, let's say, 20 sites. Okay? But there are way around, so you can still compute a lot of stuff. Actually, even solving these equations is an endeavor, so it's really a challenge. So because they are complex. Okay. So these equations have 2 to the L sets of solutions, and each set of solution is a set of up to L half, L half essentially momenta. Okay. You can imagine it's a hell to try to solve them numerically. Okay. But okay, you can do actually something called thermodynamic Bethe-Ansatz. And then thermodynamic Bethe-Ansatz is somehow tells you how you essentially construct. Instead of working with the eigenstates, you work with some rho of lambda, which is the equivalent of the n of k. Okay? It tells you how these spots, these slots are occupied. Okay? But now you see, since the density of boxes is not trivial, then rho particle, this is the density of occupied momenta, and the density of unoccupied are not trivially related to one another, okay? Like in free Fermions. In free Fermions, the holes is 1 minus rho, okay, essentially. Here you have 2 independent densities, rho hole and rho particles. Okay, and then you have a rho total, which is rho plus rho hole. So you have 2 independent set of densities. Okay, they have to satisfy some thermodynamic versions of those equations. Okay, these equations become some integral equations for this rho, the thermodynamic limit, and you can still define an entropy. Okay. So you can still define an entropy, which is called Yang-Yang entropy, which has this expression. There is minus, no, okay. Okay. Now you see that it's not the same as for free fermions because you have this extra term, which is the rho total, because rho hole plus rho particle, you have 2 independent densities, okay? So this has the same meaning, okay? You fix rho hole, rho particle, then it tells you the number of eigenstates, that number of equivalent eigenstates at fixed rho hole is proportional to e to the s L. Okay. Okay. Now we are almost done. Yes. So now we would like to do quenches in this model. You want to do quenches in this model. So for instance, you can. I mean, this is much more complicated. You cannot use free fermion techniques. Okay. But I mean, there has been by now it's 20 years or something like that people worked on that, and there have been incredible successes. For instance, thanks also to Miros, to Tomasz. Okay, so this is really one of beautiful piece of physics in the last 20 years. So, for instance, if you take the quench from the null state, so I mean, you can argue that you can show also in numerics that the system reaches equilibrium state, which is a GG. Okay, but because the model is integrable. Remarkably, you can construct a GG which is defined by this densities rho and rho hole. You can construct analytically, actually, the rho and rho hole that correspond to the steady state, to the GG that describe the steady state. Okay. And from there, you can also construct the entropy, of course. Okay? Now, based on your free fermion result, you can somehow conjecture that you can somehow conjecture. This is something that we did with Pasquale Calabrese in 2017, something like that. You can conjecture that the entropy dynamics, the entanglement entropy dynamics, is described by this formula, where S is the Yang-Yang entropy of the GG. Okay? Okay, lambda is, the rapidity or momento, whatever. Okay. Here there is an interesting part. What is this velocity? I take 2-3 minutes and I'm done. So what is this velocity? So in free fermions, the velocity depends only on the dispersion of the model. Okay. So v of k is equal to derivative with respect to k of epsilon k. So it's a property of the model itself. It doesn't depend on the state from which you start the dynamics. So a beautiful thing. In going to interacting integrable systems, so there is something new. There is some new physics somehow that emerges. Okay. So here in interacting integrable systems, this Vk depends on the state from which you start. Because depending on the state from which you start, you have a different density of quasi-particles. Now, imagine you create a pair. Then this pair would like to travel. The particles would like to travel freely, but the model now is interacting. So there is some scattering with the surrounding particles. But and this is another interesting subject in itself, generalized dynamics. So what happens? So if you have a particle that travels in surrounding particles, then what happens is that it will scatter with these particles. And you can account for the scattering by a shift somehow. Okay? And each scattering will give a shift. Then you see, if the particle were not interacting, then the trajectory would be this one. But due to interaction, this velocity is modified. So it's a dressed velocity due to the scattering. Okay? And there is an equation, another integral equation that you have to use here, which tells you how the addressed velocity depends on the density of particles. Okay? But the remarkable fact is that the effect of scattering is just addressing. Okay? And this is due to integrability. Because in integrable systems, there is no ultimate way of defining what an integrable system is, but a property somehow is that the quasi-particles preserve their identity. So if they preserve their identity, what can happen? The only thing that can happen is that there is a shift, okay, in their trajectories. Right? So yeah, I regret. I'm sorry that I cannot tell you more. This is, quite interesting. But yeah, so we have to stop here. So. Thanks for attending, and I hope you got some interesting physics and some ideas, okay? Thanks.
Thank you very much. So if there is a question, please.
I do understand that the velocity depends on the density of states because of the interaction, but the densities will also change, right? The density of states will change after the quench. So
Yeah, okay. If you want, I'm cheating a bit, but not so much. So what will happen is that when you start doing the dynamics, there will be some relaxation mechanism at play, okay? And essentially, at least at long times, you can describe, if you want, the dynamics itself by using the steady state value of the density, okay?
There you plug in the final.
Yeah, the final, yes.
Okay, so let's. Okay, there's one more question.
Mm-hmm.
Probably question is not about calculation, but you calculated a pair correlation function and then managed to relate it with the entropy. But in classical statistical physics, pair correlation function is not sufficient to find the entropy. It's not enough.
But in the first part, I mean, in the first part I did with calculations with free fermions. In free fermions, it is enough.
This is because of the free?
Yes, because the Wick's theorem holds, and then all the information about any quantity is contained in the two-point function. Yeah. In the last part, when you consider interaction, then this is not true. Yeah. In fact, there is no relationship between the Yang-Yang entropy and, let's say, two-point correlation functions.
Okay, so maybe this last question. Could you comment on the confirmation of this formula from the point of view of numerics?
I mean, numerically, numerically you can do a quite fairly large set of quenches in XXZ. There is a class of states for which you can compute. You can compute the GG and compute all these quantities. So what are the subtle points? The subtle points are first of all, who told us that this pair structure survives in interacting integrable models? This is an assumption. Okay. So this actually seems to be also related to the fact that you're able to compute stuff analytically for the quench, okay? But, okay, this is a bit tricky. Okay, in XXZ and all versions of XXZ, there are numerical confirmations of this with the limitation that you have with DMRG, because DMRG doesn't allow you to get long times. Then there is a very nice model that it's a great model. I really love it. So it's, Tomasz told about it. So it's the Rule 54 or Bobenko chain. So and it's a kind of it's a cellular automaton model that somehow you can view it as really the toy version of a Bethe-Ansatz solvable model. So it's the property of this model is that the dynamics is quite simple, but the model has a non-trivial scattering, which is actually kind of this form. And in that model, you can perform analytical calculations, and then you can actually prove this formula. Okay? This formula has been proven there. So, but the story is actually far from closed. Okay? Because, an issue that I would have liked to discuss, I think it's quite interesting, is so in free fermion models, I showed you that you can compute any function of the reduced density metric, essentially. So then, in particular, you compute von Neumann entropy. You can also compute Rényi entropies, okay? And for them, the same formula works. If you try to do the same, meaning to apply the quasi-practical picture to Rényi entropies in interacting integrable models, you run into trouble. The trouble is essentially that when you take trace of rho A to the n, this is not such an innocent operation, because this power n, if you think, let's say, of the thermal ensemble, it multiplies the temperature by a factor n. Okay? So it means that in the language of root densities, it completely changes the root density. So this object, actually, you can compute the steady state value of the Rényi entropies. And this is something that I did in the past. It was actually very nice. I really enjoyed it. So the steady state you can compute, but then when you try to compute, so the point is that the steady state depends on a thermodynamic macro state that is not the same macro state that describes local observables. It's not the GG that you use to describe local observables because of this factor n. For free fermions, this is not a problem because you can somehow relate the two. There is a functional relation between the two, so this is not a big issue. But for interacting integrable models, you need a different macrostate. And then let's say that you want to build this formula. Which velocity should I use? The velocities of the original macrostate, the velocities of the new macrostate. And then if you try to compute the density of any entropies, that turns out to be negative. I mean, it's not positive for any values of rapidities. So you see, it's kind of difficult. But then again, yeah, I close. So thanks to the Rule 54 model, so we got an idea how to build the formula for the Rayleigh entropies. So there is a formula that tells you how the Rayleigh entropy grow with time. But this formula is still a hydrodynamic formula, but it doesn't have an interpretation in terms of pairs of quasi-particles, okay? So, I mean, I would say that, yeah, let's see what the future gives us.
So we will have